Hello friends, today we are going to study the analysis of trusses, that is unit number 3 of subject finite element analysis and simulation techniques. In that we are seeing the two-dimensional analysis, that is first we will see the analysis of trusses. Okay, as we know that truss is two force members that is made up of bars which are connected at the ends by the some kinds of joints. Okay, so every element has uh, either tension or under compression. Okay, so stresses can be classified as plane stress and space stresses. Okay, so we will continue with plane stresses. See in the uh, diagram given over here, these trusses has uh, two values of deflection. Okay, as it is two dimensional analysis, it has two components of what we can say displacement at every node. Yeah, as you can see, q1, q2, q3, q4, q5, q6, q7, q8 and up to q14. Okay, so why it is so? Because q1 is the deflection of node number 1 in x direction, and q2 is deflection in y direction at node number 1 itself. At node number 2, the deflection in x direction is q3 and q4. At node number 3, the q5 is deflection in x direction at a node number 3, and q6 is the deflection at a node number 3 in y direction. Likewise, we can see for each and every node there are two components of displacement. Okay, so we will see there are always some assumptions what we can say with every finite element analysis. Okay, so there are some assumptions also we will see about the stresses. Okay, truss element is only a prismatic member, that is cross sectional area is uniform along its length. Okay, so we are considering that at every point it has a same cross sectional area. Okay, the next assumption is that it should be a isotropic material. Okay, as we are dealing with ideal conditions, so we are considering it as a isotropic material. Constant load we are considering here, that is load is independent of time. Okay, it has only magnitude. Okay, so it is not changing with the time. So also we are considering a material as a homogeneous, so properties are not changing anywhere. So a load on stress can only be applied at the joints. Okay, also we are considering that due to the load applied, each bar of stress is either induced with tensile or compressive forces. Okay, and we are considering also the frictionless pin joints, and also we will see the self weight of bar is neglected. If we consider element number 1 to any element, we will take this one element over here. This one element has node number 1 and 2. So as we can consider, there is a angle theta with the horizontal for this element. Okay, if it is translated at what we can say, after deflection, the new position of that element may be it at this position. Okay, so we have uh, taken some deflection q1 and q2. Q1 in x direction and q2 in y direction. Okay, so translated, or what we can say, deflected position of that element is shown in green color. Okay, so first we will see the dimensioning, or what we can say, nomenclature. Okay, so at node, at this element we are seeing that this position one node is going to change to this point. Okay, so it is changing its position in x direction equal to q, and in y direction equal to q2. So if we see this diagram, we can compare this with uh, these distances. Okay, as it is q, sorry, as it is theta, which is a angle between this element and horizontal. So it can be q1 cos theta, and here it may be q2 sin theta. Okay, because we have considered it as a q1 and q2. Similarly, at node number 2 we can see it is q4 and q3. Okay, so for further calculations, we will resolve this component, or we can see we have considered the distance, uh, linear distance between the node number 1, original position of node number 1, and deflected position of node number 1. In between we have considered q1 dash as a distance between, linear distance between them. Okay, so as we know that q1 dash will be equal to q1 cos theta plus q2 sin theta. Okay, q1 dash is equal to q1 cos theta plus q2 sin theta, and q2 dash is equal to q3 cos theta plus q4 sin theta. We can see over here L is equal to x2 minus x1 divided by length of the element is equal to cos theta, and m is equal to sin theta, that y2 minus y1 upon length of the rod. And here we can see the length of the rod we can find, that is by the formula under root of x2 minus x1 square plus y2 minus y1 bracket square. Okay, here we can put cos theta as a L and sin theta as a M. The equation will be like this: q1 dash is equal to q1L plus q2M, q2 dash is equal to q3L plus q4M. We can convert this system of equation into matrices, that is deflection matrices, with like this one. Q1 dash, q2 dash is equal to lm 00 lm, and the q multiplying elements are q1 q2 q3 and q4. What we can write here in short form as q dash equal to l into q matrix, where is the called as a transformation matrix that is used for local global correspondence. Okay. Strain energy we know already, it is equal to half q transpose k into q. So for truss element we can write it, rewrite as is as q, u is equal to half of q dash transpose k into q dash. Where q dash is equal to l into q, we already found it. Okay, so q q dash transpose is equal to l dash transpose into q dash transpose, so that you will be equal to half of l transpose q transpose k into l into q. So half of q transpose, we can keep q transpose aside, and we will write it as a l dash k into l. Okay, so it will become k. Okay, so the final equation will be half of q transpose k into q. So kt is the stiffness matrix of the truss element, and we will find it. See this, kt is equal to l transpose k into l. L we know that, and l transpose will be like this. And key equation, we already know that a into e divided by l, where a is the cross sectional area, e is the Young's modulus, and l is the length, and 1 minus 1 minus 1 1. If we arrange these three matrices in this order, then we will get, after multiplication, we will get this kt, that is element stiffness matrix for truss element, that is l square lm lm m square. Okay, so we can see this arrangement like this one. Okay, so suppose this one is one element, l square lm lm and m square, same set of elements are arranged in this order, so that we can easily keep in mind this arrangement. This one is 1, and this one is minus 1, like, okay, multiply with minus 1, this one multiply with minus 1, and this one is multiply with 1. As already we know that the stress component for stress elements are sigma is equal to epsilon into E, that is strain into modulus of elasticity. But strain is equal to, we know that, V into Q dash. Okay, so Q dash is equal to T into Q, where B what is B? It is 1 by L into minus 1 1. Okay, that sigma, that is stress, is will become E upon L into minus L minus M, Lm, and this one is your deflection matrix. Okay, so now how to calculate the direction cosines? This is a big question, as already we have seen or quoted that this one node has coordinates x1 and y1. This node number 2 has coordinates x2 and y2, and the difference is shown over here, x2 minus x1 and y2 minus y1, and this is the length of the element. Okay, so we can see here uh, L we have considered as a cos theta. Okay, so here cos theta will be equal to cos theta, that is equal to adjacent side, that is x2 minus x1 divided by le, x2 minus x1 divided by le, and here m, that is sin theta is equal to, sin theta is equal to opposite side, that is y2 minus y1 divided by le. So we can calculate the length of the element as we will see, or we can use the Pythagoras theorem for this. Okay, L is equal to under root of uh, x2 minus x1 bracket square plus y2 minus y1 bracket square. Students, with this we have seen how to generate the stiffness matrix, and we have generated it with the simple expression, or what we can say, simple method. Now we will see some examples on same topic, uh, and we will try to solve the problems by using this stiffness matrix. Thank you, thank you.